So far in our consideration of thermodynamic properties of gases, we've constrained ourselves to talk about ideal gases. In this part of Lecture 4, we're going to talk about real gases. Let's start out with an experiment that was done by Joule-Thomson back in the late 1800s. This is the system, this is the initial state, this is the final state. One has a gas right here at some pressure, volume, and temperature on the left. Here, let me try to change the ink color here so we can see that better. We have something here on the left. It's pressure, volume, and temperature, some gas here, and has some volume. Over on the left, in the initial state, there is no volume here, and these two chambers are separated by a porous plug. The porous plug allows one to push on this gas and have the gas over here be at a different pressure, and of course the volume will change as the pistons move. And what Joule and Thomson did was to measure the temperature, on both sides of the system here. All right. Furthermore, this whole thing here is insulated, so there's no exchange between of heat between the system and surroundings. The porous plug is also insulated, so this means that this can be at one temperature, and over here in the other chamber it can be at a different temperature. So the experiment is one pushes on this piston to push the gas through this porous plug. The porous plug allows one to have a different pressure on the right hand side. So at the end of the experiment, the volume here has been reduced to 0. The volume here has been expanded, and we have a different pressure, different volume, and a different temperature. So we use 1, the subscript 1, to indicate the left-hand side, the chamber on the left-hand side, and the pressure, or the subscript 2, to indicate the PV and T on the right-hand side. Okay, so let's analyze this thermodynamically. All right, this is essentially just what I said. We're going to show this process is isenthalpic. The enthalpy on the left in the left-hand chamber doesn't change in the right-hand chamber. And then we can ask this question, should it be positive or negative? So we're going to go through this derivation down here. Okay, so just to refresh our memories, here's the system, the initial state, final state. We pushed all the gas through here. There's a different pressure, volume, and temperature on the right-hand side. All right, let's start this by looking at the first law of thermodynamics. That's a good one. So delta U is equal to Q plus W. And now this is equal to W. We're assuming that's an adiabatic process. So in other words, all this is insulated here, so there's no heat flowing to or from this chamber, and down here this is all insulated, no heat flowing to and from this chamber. So essentially we have two adiabatic chambers. All right, let's look at the change in internal energy, delta U. I claim that's equal to the internal energy of the second chamber minus the internal energy of the first chamber. Why is that? Well, initially there's no volume, no gas over here, so the internal energy over here is 0, and we have a certain internal energy U1 on this side. At the end of the process, we have no gas over here, so clearly the internal energy is 0, there's no gas, and over here we have an internal energy. So we can calculate the internal energy, the overall internal energy change, just as this, what it was finally, and minus this, what it was initially. So 2 and 1, this is 2 right-hand side, 1 left-hand side. Let's look at work. Well, work will be equal to the work done on the left-hand side, U1, plus the work done on the right-hand side, U2. Now this work will be different because we have different pressures and different volumes. So when you compress this, we do a certain amount of work. When this is expanded, it'll do a certain amount of work, but those two work could be different because we have different pressures and volumes. Okay, so let's actually calculate the total work. On the left-hand side, this will be the integral from the initial volume V1 to 0. Remember, we're going to 0 volume here on the left-hand side. of the pressure, P1, times dV, and there's a minus sign in front of that, minus the integral, and the left-hand side we're starting at, the right-hand side we're starting at 0 and finally ending up at volume V2, and this is the pressure on the second-hand side times dV. And we're going to assume that the pressure here will remain constant as we squeeze this, and the pressure here will remain constant as we expand this. So we can pull out the pressure here, constant pressure process. This will just be P1. The integral, and put a minus sign there, V1 to 0 of dV minus the integral of 0 to V2 of, let's pull the P2 out here, times dV. And we evaluate this as it be 0, P1 times 0, that'll be 0, minus, so this comes out to be a positive P1 V1, minus P2 V2. All right, so that's the work done, the total work done. On the left-hand side, the compression. On the right-hand side, the expansion. It's just P1 V1 minus P2 V2. All right, so let's equate this to delta V, which is U2 minus U1. Okay, so U2 minus U1 is equal to, we said P1 V1 minus P2 V2. If we rearrange this, put the 1's on this side, the 2's on this side, change signs and so on, we have U1 plus P1 V1 is equal to U2 plus P2 V2. All right, this is the enthalpy on side 1. This is the enthalpy on side 2. Enthalpy does not change. So this implies that that particular experiment is done under isenthalpic conditions. Isn't that interesting? Okay, so this is an isenthalpic process, squeezing this, and then making it come out here at a different pressure, different volume and temperature. Okay, and get rid of all that stuff. That's kind of interesting. But wait, there's more. Let's go ahead, excuse me, and look at this. We said that H is in general a function of temperature and pressure, and for an ideal gas, H is a function of temperature for an ideal gas, not a function of pressure. And that means that if you have a change in pressure, there'll be no change in enthalpy. However, this now is for real gases. We're considering real gases, so we don't have to consider the fact that it's only a function of temperature. We should consider it's a function of pressure also. So with that understanding, we can say that the differential change in H is how H changes with temperature at constant pressure times the change in temperature, plus how H changes with pressure at constant temperature times the change in pressure. This we know. We define this, let's define it as heat capacity at constant pressure. That's how H changes with T. This is how H changes with pressure, constant temperature. All right, let's equate this, plus how H changes with pressure. I forgot the dt there. Yeah, at constant temperature times dP. We said that this particular process, we're going to focus on the process, this is a isenthalpic process, so that means that dH is equal to 0. Or in other words, Cp dt is equal to minus how H changes with pressure at constant temperature times dP. We can rewrite this as how H changes with pressure at constant temperature. we'll take the dP over here, so that's equal to Cp, how temperature changes with pressure at constant enthalpy. Oh, how temperature changes with pressure at constant enthalpy. Oh, look, we can just put a thermometer here and a thermometer here and measure the temperature change and correlate that with pressure change. In fact, this quantity, how temperature depends on pressure, constant H, is given a special symbol, mu, subscript JT, and this stands for Joule-Thomson. So this is the Joule-Thomson Coefficient, how T changes with pressure at constant enthalpy. All right. Joule-Thomson Coefficient. Thomson is also known as Lord Kelvin, for which the unit of absolute temperature Kelvin is named. All right, so there we have the Joule-Thomson coefficient. Now let's look at that. End of slideshow. Well, just hold on a second. I'll create some more things to do here. 1 second. All right, so let's rewrite the Joule-Thomson coefficient up here. Here we go. Changing color. So we said the Joule-Thomson coefficient is defined as how temperature changes with pressure in an isenthalpic process. Now, why are we talking about real gases? Well, you know, you can have like liquid nitrogen and liquid helium and liquid oxygen and things like that. The way those are industrially produced is exactly the kind of, well, let's go back here. Let's go back here. And finally, let's go back here. There we go. The liquefaction of real gases, oxygen, helium, nitrogen, and so on, are actually produced by this Joule-Thomson kind of experiment. Interesting. So let's look at conditions under which we want cooling of gas. We want to cool the gas so much by expanding it. Let's see, so we have a gas under some pressure, and we're going to shoot that out a porous plug, and we want the dT to be less than 0. And that means that this implies that dP will be less than 0. So the idea is you have a piston here, some sort of porous plug. Here's a piston. We're going to shoot the gas out here, and we want this to cool the gas. We want to cool the gas, we want dT less than 0, which means we're going to have a pressure drop. The pressure here is less than 0. So this implies if you want to cool the gas when you expand it, you want to have the Joule-Thomson coefficient to be greater than 0. You want a positive Joule-Thomson coefficient. It turns out if you actually measure this, how temperature changes with pressure in a constant enthalpy process, if you actually measure that, what you find is that it varies with temperature. Okay, and we said that we need a Joule-Thomson coefficient positive. So let's look, say, at helium, and this is right down here. This is room temperature. So if you just take helium at room temperature and you compress it and then shoot it out a nozzle, the Joule-Thomson coefficient for helium at room temperature is negative. In fact, it's just the opposite. Now when you expand the gas will heat up instead of cool down. So you can't liquefy liquid helium just by compression expansion process. Let's look at argon. Oh yeah, here's argon. Yeah, it looks like that's okay. It's all positive way up here. So at room temperature, argon has a positive Joule-Thomson coefficient. Also nitrogen, so you just take air. But for things like hydrogen and helium, which have a negative Joule-Thomson coefficient at room temperature, what you have to do is to cool those down so that the temperature or the Joule-Thomson coefficient becomes positive before you can actually liquefy them by this compression expansion process. Here, the temperature at which the Joule-Thomson coefficient goes from negative to positive or positive to negative is called the inversion temperature. Inversion temperature. So for hydrogen, it's 200 Kelvin, and for helium, it's way down here around 30-40 Kelvin. So you got to cool the gases down to there before you can liquefy them by compression expansion. Okay, so that's real gases and practical use of real gases using a Joule-Thomson coefficient. Take a gas, make it into a liquid.